So let's look at a particular type of basket option, the exchange option. So it involves two stocks, and when you own one of these exchange options, you own the right to trade a quantity, Q2, a number of stocks, S2, for a Q1 of S1. All right, so to straighten that out, you give Q2 of S2. So Q2 is the number of stocks you give, and S2 is the price of those stocks. So Q2 S2 is how much money you're giving, and you're getting the number one stocks. You're getting Q1, the number of shares, and S1, the price per share. That's how much value money you're getting. So we're pricing an option here. It depends on the two stock values, S1 and S2, and it also depends on time. The payoff at expiry is, well, you get the Q1 S1 and you give the Q2 S2, so it's the difference. Or zero, right? It's an option, so you only do this, you only exercise it if this piece is positive. Otherwise, it just expires worthless. So we want to price this particular basket option, but it's only got two stocks. So we grabbed our multidimensional Black-Scholes equation, and I made n is equal to 2 here. And let's see if we can kind of clean this up, simplify this up a little bit. We can price it. We've got our multidimensional solution here. There's only two stocks, so I only have to integrate over 2, 1, and 2. So let's clean this up and see if we can get our integral. Our payoff then, I've got the payoff here. It's, well, okay. I'm going to put the payoff in a second here because I want to draw the region over which we're at. Since there's only two stocks, our correlation matrix is just this 2 by 2, and we've got the two alphas here. Okay. Our determinant is just going to be 1 minus rho. There's only one row, so 1 minus rho squared. We can put that in for our determinant here to simplify. And n is equal to 2, so 2 over 2, 1. So we've simplified things up. I just need to worry about this. I just need to worry about these endpoints here. So it's where this Q1 S1 and Q2 S2 are positive. So let's draw that. So if I make this the S1 and I make this the S2, then I'm looking for Q1 S1 minus Q2 S2. I want to know where that's positive. So let's make this as a line. So that's going to be Q1 over Q2 S1. So we've got a line that goes through the origin with slope Q1 over Q2. And we're talking about exercising here, where the thing I get, the S1, is worth much more than the thing I give, the S2. So now we're going to integrate then, instead of from 0 to infinity both pieces, let's do the S1 first. Now let's do the S2 first. S2 is always going from 0 to the line. So our integral for S2, I'll do that first, is going from 0 to the line, and the line is what, Q1 over Q2 S1, and then Y1 is going from 0 to infinity. Okay, so we've got our endpoints here. I'm keeping this 0 to infinity. We're switching the order for convenience, and this endpoint is Q1 over Q2 times S1. So when we integrate with respect to y, we're going to sub in, we're integrating, but that's going to be y's, right? We're subbing in, we're going to integrate with respect to y2, sub in from 0 to, remember, we're integrating over in y's. Okay, we can do that, and now we're only in the region where this expression is positive, so I can write, instead of writing payoff here, I can put in what the actual positive piece is. And I want to write that in terms of the y's. And it looks, it really, I kind of feel like this doesn't look too bad to integrate, right? We're cleaning it up. Integrating with respect to y2, there'll be a ln, and well, okay, it's not as easy as we think because there's y's up here in the e to the minus. So, okay, it's not as easy. We could, oh, and let's clean this up. Our expression is only for those two stocks. So, we understand what this exchange option is. We see where in the region we would want to exercise it. We use this to set up the integral, and if we want, we can do Monte Carlo integration on this. And it's tempting that we might just be able to integrate it analytically. We won't, but it kind of looks like we might be able to. Monte Carlo would be the best way to integrate this. But now I want to introduce an idea here. I'm only going to, if Q1 and Q2, they're the ratio of the exchange of the stocks. So I'm going to introduce another variable that has to do with the, so what I mean by the ratio is, what if I was giving, if stock 1 was $40 and stock 2 was $20? That would be the same, there would be the same decision being made as if stock 1 was $10 and stock 2 was $5, right? It's the ratio of those. It's just whether or not, so whether or not this piece is positive is, it's really, where am I? It's really, is S1, how is S1 and S2, is that bigger or smaller than Q2 over Q1, right? Is this ratio bigger or smaller than this value? So, inspired by that, let's make this its own variable, R, for the ratio. So when I do that, I'm making a new variable, R, which is just the ratio of the stock prices. I've got my differential, my partial differential equation here. It's only 2, so let's, before we jump into this ratio, let's just clean this up a little bit, right? Like this first piece, I don't really need a summation. It's really just it's when I is 1, get rid of this, plus when I is 2, right? I mean, first I is 1 and then I is 2. I don't think I need a summation there. Let's get rid of it. And likewise here, this plus a half with this sum. I'm looking at this piece in here. I is 1 and then it's 2, j is 1 and then j is 2. Really, it's this piece, but there's 4 of them. There's 2 choices for I, 1 and 2. There's 2 choices for j, 1 and 2. So let's just put those 4 pieces in there. So let's go with the 1 and the 1. Oh, that's the correlation between stock 1 and stock 1. Row 1, that's just 1, so I'm just going to get rid of it. And this is v sub 1. 1 and 1. Okay, so there's the 1, 1 piece. And, well, okay, sigma 1, sigma 1. Let's just write that as sigma 1 squared. So there's the 1, 1 piece. Next, we'll write the, well, 1, 1, now the 1, 2 piece. So I need this, where it's 1, 2, 1, 2, 1, 2, and 1 and 2. All right, now let's do the 2, 1 piece. Oh, but the 2, 1 piece, that's going to be 2 and 1. This will be the same, right? The correlation between 1 and 2 is the same as the correlation between 2 and 1. That's why this correlation matrix is symmetric. So the 1, 2 piece and the 2, 1 piece are exactly the same. What about the derivatives here? The derivative with respect to stock 1 and then with respect to stock 2, or the other way around? Clairaut's theorem says they're the same thing. So I'll just double it instead of rewriting it. So now the last thing I have is the 2, 2 piece. But the 2, 2 piece is going to be like the 1, 1 piece, the correlation between stock 2 and stock 2 is 1. So that's just going to be with all 2's here. All right. So rewriting it, that just makes it a little bit nicer looking, simpler than this. And oh, this is supposed to be inside the half bracket. So that's expressing all these pieces here. Okay, so that's a little bit, I mean, it doesn't have the summation sign, so a little bit easier. Let's go back to our introducing our new variable. I don't want to do that. Our new variable here, which is the ratio between the 2 stock prices. And I want to, it's like a substitution, solving an integral. I want to do a substitution, but I want to substitute into this equation here. Let's move these s's over just to make it look more friendlier. So I need the partial derivative with respect to time. I need the partial derivative. Well, if I do this substitution, let's go right back to what the payoff is then. And I'm going to modify this payoff. It's the maximum of these values. I'm going to factor out a Q1 here. So if I take this max of 0, and if I factor out a Q1, it's still the maximum of those values of the It's just a different way of expressing it, but it's the same payoff function. And I'm going to do the same thing, but I'm going to factor out an S2. Now I've expressed this payoff as the number Q1 times the stock price S2 times the maximum of 0, or how the ratio compares to the ratio of those, the quantities that I get. And now I'm looking at this piece here. Let's price this. Let's price an option that has this payoff, and that's our ratio. So now I'm pricing something, and let's call it H. H is a function of R and time now. So it's only dependent on the ratio. If I could price this, if I could solve this equation, so in other words, get a formula for H, then I'll just multiply it by Q1 and S2, and I'm done. So I'm going to switch everything over to functions of that ratio. So if I'm differentiating with respect to S1, chain rule, that's like differentiate with respect to R times differentiate R with respect to S1. Likewise for S2. And what is the derivative of R with respect to S1? Well, I've got the formula here with R. That's just 1 over S2. So the derivative of R with respect to S1, keeping S2 as a constant, is just 1 over S2. All right, well, let's just put that on the outside there. Let's do the same thing here. I need the derivative of R with respect to S2, treating S1 as a constant. So that's going to be a negative, S1 is a constant, a negative S1 over S2 squared. So this is going to change into a negative S1, that's the constant, over S2 squared. Alright, this is going to look funny, S2 squared, there's a 2 on the top and a 2 on the bottom, but the top one is a squared piece. And let's put that on the outside then. So now I've got this derivative that if I differentiate something with respect to S2, that's what happens. Now I need, okay, I'm substituting in here, right? I have the derivative with respect to S1, derivative with respect to S2. I need all these second order partials with respect to S11, 1,2, and 2,2. So I need to build those pieces. So I need the second order derivatives. So let's take a look here. To get the derivative of S1 and then S1 again, that's, well, I've already got the S. Take this and differentiate it again with respect to S1. Okay, so I'm differentiating this with respect to S1. Well, that's a constant with respect to S1, so it's just there. And now I need to differentiate this with respect to S1. the rule that we made is when you differentiate anything with respect to S1, you take that thing, multiply it by this, and then differentiate it with respect to R again. So this one's a constant, this one comes from my rule, and I'm differentiating with respect to R again. So it's already been differentiated with respect to R once, now it's differentiated with respect to R twice, and I guess 1 over S, we can make that a 1 over S squared. So here's our second derivative then, S1. Let's get, let's get S1 and then S2. So that's going to be when we differentiate with respect to S1 and then S2. Doesn't matter the order because of Clairaut's theorem. So I got choices then. I can take this, which is the derivative with respect to S1, and differentiate it with respect to S2, or I can take this, which is the derivative with respect to S2, and differentiate it with respect to S1. I think that's easier. Let's take this and differentiate it with respect to S1. Now it's going to be product rule, so derivative of the first with respect to S1, well, that's just 1. Leave this alone, plus leave this alone. Now I'm differentiating that piece with respect to S1. When you differentiate something with respect to S1, you multiply by 1 over S2 and then differentiate that thing with respect to R again. So I need another one of these, and then this becomes our second derivative. Okay, so now I've got the heterogeneous partial. Let's get the, what do I need? I need the S2 one. Okay, here's already the derivative with respect to S2. I'm going to differentiate this with respect to S2. Okay, this is going to be messy because I got to do product rule. Let's do derivative of the first. So that's like S2 to the minus 2. The minus 2 comes down. Subtract 1 from the exponent. Okay, so there's the derivative of the first piece with respect to S2. Leave the second alone. Leave this alone. Now I'm differentiating this with respect to S2. What's our rule when we differentiate with respect to S2? We multiply by this piece. So, and differentiate again with respect to R. All right, let's clean this up. It's a negative and a negative. That makes that a positive. And this is to the fourth. And that's S1 squared. Okay. There's our second order partials and our first order partials. So we're all set now. We've got all the pieces that we need to substitute into this Black-Scholes equation. Right, I can substitute in for all these partials. Oh, I didn't do the derivative with respect to t. The derivative with respect to t is just going to be the derivative with respect to t. And okay, we got a little bit this, we can clean this up. 1 over S2 and S2, we can make that an S2 cubed here. Just trying to make things as simple as possible. All right. Now remember that we're changing what V is to Q1 S2 H, where H is a function of the ratio and time. So let's do all our substitutions here then. Okay. V is going to be Q1 S2H. So let's do our substitutions. There's just our regular V. V with respect to T is going to be, well, that's a constant with respect to T. S2 is a constant with respect to T. So this V with respect to T, that's just going to be with the time derivative there. Now let's use all these derivatives that we made. So here's our derivative with respect to S1. So that's here. If I'm differentiating something with respect to S1, I multiply by 1 over S2 squared and then differentiate it with respect to the ratio. So the derivative of this with respect to the derivative of V with respect to S1 is going to be, that's a constant, times the derivative of H with respect to S1. And when I differentiate H with respect to S1, it's like 1 over S2 times H sub R. So I'm going to put that in. H sub R. So there's my, oh, and nice, S2 and 1 over S2, that cancels out. It's already simpler. So now the derivative with respect to S2. Okay, if I'm differentiating V with respect to S2, differentiating this with respect to S2, that's going to be Q1H, I'm doing product rule, Q1H plus Q1S2 the derivative of H with respect to S2. If I differentiate with respect to S2, and again, this S2 and one of those S2s cancel. So let's do that. And, oh, S1 over S2, that's R. Capital R, as not to be confused with risk-free rate of return. So, okay, that's cleaned up then. Now, that's the two partials. Let's do these other, I gotta put in for this one, I gotta put in for this one, and I gotta put in for this one. Now, the derivative of this with respect to S1 and then S1 again is going to be, so I'm just looking at this piece here, that's with respect to S1, those are constants, so they stay the same. Now I just need the derivative of h with respect to S2, S1 and S1. When I differentiate with respect to S1 twice, it's like 1 over S2 squared times h with respect to r twice. So I'm using this rule here, S1, S1. And we can do some cleanup, right? This S2 cancels with one of those S2s, and then, yeah. All right. I'm going to pause the video, substitute these other two pieces in here, so you don't have to watch me do algebra, but it would be good if you check them. If while I paused, you check them to see what you get as well. But, I mean, that can be another time. So I'm going to pause. So here's all our derivatives, and I mean, I did a bunch of algebra. I paused it and did a bunch of algebra. You should check these. It's chain rule, and they simplify down nicely. And we could even, in fact, before I sub them in here, maybe we can clean them up a bit. Remember that R is the S1 divided by, R is S1 divided by S2. So I could write this as R divided by S2 if I wanted to. This I could write as R squared divided by S2. Let's put these pieces in then. I already subbed in for the V sub S1, S1. Let's sub in for the S1, S2, which is this middle one. And let's see how nice this simplified down. This next one, the S2, S2, also simplifies down quite nicely. Okay, now everything is in terms of H. There's no more V's. And we can get a lot of a simplification happening here. Let's look at, so let's clean stuff up. Here I've got an RQ1S2H and an RQ1S2H. So these pieces cancel. Now, that's going to make this here and just have that as a minus. Now, look for another piece that has an R in it. Oh, here's an R. Remember that R is S1 divided by S2. So R, or I'm trying to tidy this up here. R times S2 is S1. So I can cancel this to be S1, and that means that this piece exactly cancels out this piece. So gone. Well, that got a lot simpler. And notice there's no more little r in here at all. There's no more interest rate in this at all. Maybe we can do a little bit more tidying up, right? I've got three pieces here with this HRR. Let's do some tidying here with this HRR. In fact, I think I can just factor that HRR right out of this huge bracket. So let's do that. I'm going to take this all the way to the outside, to each one of these. Now, is there any other cleaning up? Well, I can cancel this S2 with this S. Oh, no, that's S1 squared. What other sort of tidying up can I do? I can cancel one of these S1s. I can cancel that S2 with that S2. I can cancel two of these S2s with two of those S2s. What can I factor out here? I've got a Q1 in each one of these pieces. So let's take a Q1 to the outside. Okay, now I can make this an R, and I want to change everything into R's. I can make this one an R. So I have an S1R and an S1R, and I can make, oh, this an S1R as well. That means I can factor an S1R out of these pieces. S1R. Now, one last, I don't like these S2s and S1s and R's here. I'm going to divide everything in this equation by S2. And because this side is 0, I can do that. So I'm dividing everything by S2. Divide that by S2. Divide this piece by S2. That makes S1 divided by S2. That's another R. Oh. I'm almost there. In fact, we can divide the Q1 out, right? With that 0. And, oh, I lost a minus sign in here when I canceled out that piece. So now, what do we got here? This looks like, the heat equation, but it looks like our regular Black-Scholes, but our regular Black-Scholes without an interest rate, or the interest rate gone, and without the S V sub S piece as well. So it sort of looks like we can, if I call this, so I'm going to do a substitution here. If I call sigma equal to, I already used sigma. I need another sigma. So I'm going to use the sigma we have, but I'm going to put a bar on it because it's like it's not the exact sigma. It's this. It's going to be the square root of all this stuff here. If I do that, then my equation becomes very much simpler. And this we can solve. This we already have the solution to. So here's the equation that we're trying to solve for h, and here's h's payoff. It's the maximum of 0 or r minus q. It's like a call option where this is the stock and this is the strike price. So let's compare then our, here's our regular Black-Scholes compared to the equation we got. We got v of t, h of t, sigma squared over 2, sigma bar squared over 2, r squared, s squared, second derivative, second derivative. We're just missing these pieces here. It's like if I set r equal to 0, it's like a call, right? Where the asset is the S or the R up here, the strike price, the E is the Q. So we have a solution for this. I can use my call equation. So H is going to be equal to our call equation, but instead of E, it's Q1 over Q2. And the R is supposed to be 0. Our risk-free rate of return is 0. There's no R in here. So e to the 0, that's 1, that's gone. And our S is R. Okay, so let's clean up our D1s and our D2s here. Okay, we got that, so let's get rid of that. Our D1's going to be, there is no R. There is no R. In fact, let's just keep it like that. There's no R, but there's still a negative, right? And our E is the ratio in the Q. So we have that. Our S is our R. And our sigma has the bar on it. It's this sigma. But otherwise we have this sigma 2 has a bar on it. But otherwise we have a solution. And once we get the H, okay, remember, once we get the H, our V that we really wanted to get is all the way up here, Q1S2H. So the exchange option price is times H, so that's going to be equal to, when I multiply it by this H here. It's Q2 divided by Q1. Duh. So that was copied down from the top part, are different. So let me just switch these around. Q2 divided by Q1. That's our E. Yeah, it looked funny because when I multiply this Q1 through, it's supposed to cancel this Q1 here. So let's multiply that through, zip, and then it cancels that Q1 on the bottom. Oh, and since we're multiplying, R is S1 over S2. So when I multiply the S2 through, it's going to cancel that S2 off the bottom and just make this S1. Okay, now I'm happy because we've got an actual answer, right? We can price an exchange option, noting that so our sigma, our volatility of the ratio, is this expression, but we've got a closed form solution. We use the page 200 formula. So this is nice. We'll do an example. We'll do a quick example in the next video, but it means when we do our Monte Carlo integration here, we'll know what the answer's supposed to be. We'll be able to check our work.